Hello there, function folks. Welcome to the first part of lesson 1.10, which is on applying polynomial equations. We've got a double lesson today, and they're two small ones. The 3-minute review is the sheet called inequalities, and it's right there. And essentially, if you follow the instructions and get something out of it, that's awesome. That's what you're supposed to do. This right here is where this inequalities handout will come in. This video is on applying polynomial equations, and the next couple of days we'll be talking about applications of the things we've been talking about in this unit, where it might fit in the real world. But this 3-minute review, you can do it, or you've done it already, and that's awesome. But we won't sort of take that up until till part 2. Part 1, applying polynomial equations, solve problems involving applications of polynomial functions. So we've been doing all this stuff about factoring and graphing and solving polynomial equations without sort of talking about where they might fit in the real world. This whole idea of fitting in the real world, essentially, we're going to use our math to model real life situations. And here's the types of questions that we're going to run into in the next couple of days of applying polynomial equations. We could be given an equation that represents something and just asked to solve it. Now, this one is not one that's not that new or different. Essentially, the inputs and outputs represent something in real life, and then all we have to do is solve it. What's more challenging for us, and we won't see one today, but I'll talk about it very briefly, is to make your own equation and solve it. And we'll actually do more of this type when we get back to applying polynomial equations. We sort of take another look at it in a couple of days. But I'll show you what the second one looks like. Example 1 on page 196 is Amelia's family is planning to build another silo for grain storage identical to those they have on their farm. The cylindrical portion of those they currently have 15 meters tall, and this silo's total volume is blah, 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 blah. What are the possible values for the radius of the new silo? So notice there's no equation in here. We kind of have to come up with the equation ourselves. So how would we do that? Well, there's the volume for a silo shape, and some formulas from grade 9 that we use, and we solve it. We factored out something and then solve this using the factor theorem, or I think they might use actually technology. But this is the idea where we had to come up with our own polynomial equation given the question. We're going to practice that not only in the homework tonight, but later on, the next couple of days of class. Here's the second one of the second type. The second type is after the driver, notice that given this, after the driver of SUV applies the brakes, the position of the vehicle is given by this. So notice that time is in seconds since the brakes have been applied. And d, the distance in meters, is how far the SUV has traveled. And this function, this polynomial function, models the situation. Okay? And we are asked to solve a few equations. How far does the SUV travel after 2 seconds? So in A, what are we asked? And that's kind of the big thing, is to figure out what are we asked. How far does the SUV travel after 2 seconds? So this 2 seconds, is it the distance or is it the time? It's the time, right? So time is equal to 2. We want simply just d at 2. So this one's easy. All I have to do is substitute in the 2 in here, bash away at a calculator, and I get the answer of, where's my answer, of 54.4. So therefore, after 2 seconds, the SUV was 54.4 meters away. In part B, which is probably, it says find when d at t equals 0 and interpret your answer. All right, so it's asking me now to solve this equation. It wants d at t is equal to 0 and we want to solve this equation. Well, how do we go about doing that? Notice it's already in factored form, or close to it anyway. I can see here this gives me the answer t equals 0, and this gives me a second equation that, well, it's got decimals in it, so I'm kind of worried about that. When is that equal to 0? Well, I can just solve that because there's only one t squared. I don't have to factor it at all. I can just isolate the variable, divide by 0.1, and then square root, right? Remember, I got to be careful when I take the square root because I got the positive and negative numbers. Positive and negative square root of 140 is about 11.83. Okay, so what is this saying? This means that the distance is 0, the SUV was 0 meters away after 0 seconds. Well, that makes sense because when we started timing, it was 0. The distance was 0 at 11.83 seconds and negative 11.83 seconds. That's just purely the math, right? That's exactly when this is true. But of course, this makes us think about, hang on, what's going on here? Does this make much sense? Well, let's try a sketch. If I sketch this, I know I've got zeros at, I got zeros at negative 11.83, at 0, and at 11.83. So, and this is the distance that the SUV is away. And notice I've got a cubic, and if I were to expand that a little bit, I've got a cubic, and d at t is 2t times 14 minus 0.1 t squared. If I multiply this through, I can see that this leading coefficient is negative, right? It's negative, and so that means it starts high and ends low with these 3 zeros. So it means the sketch looks something like this. It starts high, ends low. And so what does this mean? Well, first of all, do any of these times, does this make sense at all over here? Well, this model would probably only fit after the brakes have been applied, right? After the brakes have been applied, this is the model. So notice here, t is going to be greater than or equal to 0 since the model works after the brakes were applied. Oops. But have a look at this now. So this kind of makes sense. This is the distance, right? This is the distance that the SUV is. And as the brakes were applied, the distance increases quickly at first and then more slowly. But then as the time goes on, suddenly the distance starts decreasing, and suddenly I guess the SUV is going in reverse, and then it ends up actually going backwards and backwards and backwards. This doesn't make any sense, right? I think it makes sense for the first few seconds, but after that, here, t at t is decreasing. This doesn't make any sense. The brakes start making the SUV go backwards. And so what I propose here is this model is actually only good till about there, right? Till the maximum. And then the SUV should have had the distance remain at whatever the stop, right? Here is when the SUV stops. and the distance should be constant. And so what's the domain where this model makes sense? I think over here, this model doesn't make sense. Up until a certain time when the SUV reaches a maximum distance, then it makes sense. But we don't know what that is. We have trouble finding the maximum. We know that the rate of change would be 0 there, but we don't know when that occurs. That's not till calculus that we'll find out. Here, the domain for this function, even though the original function, if I'm just talking about the math function, it's defined for any values of t. The values that make sense in this context are going to be just t is greater than 0 and less than some constant c, where c is the maximum value, the local maximum of d at t. And how do we find out what c is? Well, we have to wait until calculus. Again, we're sad about that. Okay, that was the one example that I wanted to show you. And notice that there's a lot, solving the polynomial function wasn't too tough, but interpreting it in the context of the question, there's a little more thought involved. There's some values that don't make sense, and you kind of just have to think about which ones do. The homework that goes with this lesson is just 2 questions, one from here, one from here. But remember, there is a second half of this lesson coming up next.